In part 2 of this session, we will be talking about treatment effects, statistical significance and power, meta-analysis, and forest plot. We remember the example of testing whether drinking coffee causes increase in blood pressure. So the effect of the treatment, which is coffee in this instance, is increase in blood pressure. And measuring blood pressure is what's called an outcome measure. It's the way blood pressure is measured and represent measuring the effect of it. So the outcome measure really, it is the measurement or the observation used to measure the effect of a treatment in a study. Now, there are three features expected in a good outcome measure, that the outcome measure should be and should have been shown to test the particular aspect of function that's reported to test, so it's the validity. So we really want to use a measure so that assesses pain or blood pressure or function, not something else that we're interested in. Also, it should be a test or a measure that is giving the same results regardless of how or when or who does the measurements. So it is reliability. Responsiveness, that means it has got good responsiveness for the change in the outcome, that it really tells us when there is change in outcome and in a good way. There are two types of outcome measures generally. They are objective, which means that they are measured outside the influence of the person concerned. So checking blood pressure, number of heart attacks, death rate. Subjective is the opposite, where the person who is involved can influence. So when you ask somebody about pain, it's a subjective thing to do with how they felt, how their pain is. There are also two types of outcome measures from different contexts, which is whether they were continuous or categorical. Continuous, so that we talk about pain severity, starts from 0 to 10 or 0 to 100. It's continuous, or physical function of blood pressure, as opposed to categorical. So you say the number of heart attacks could be 0, could be 1, could be 5 heart attacks. There is no sort of continuity. You can't categorical and you can sort of group them into groups. The continuous outcome measures could also be classified into interval, like temperature measurements in degrees, or differences between 20 and 30 is the same between 30 and 40. Ratio, which means whether you talk about the height or mass. Categorical also sort of divided into or classified into nominal. They have two or more categories with do not have intrinsic order, so male, female, dichotomous, or ordinal. How are outcome measures data reported? So when we measure using an outcome measure, say blood pressure or pain intensity, the way we then report that, if the outcome was continuous, say, for example, blood pressure, what we report in the group in studies, we report their mean, their average, and the standard deviation, which is the amount of variation of the raw values. So the difference in the change in the groups, or the mean difference. And what we're talking here is that if you imagine we have two groups, group A and group B. Think about the example of coffee, for example, with blood pressure. And after time, the blood pressure mean in the group A changed. And the same happened in group B. And the average also changed. The treatment effect is the difference in the mean in the two groups. Let's talk about another example to illustrate exactly the same principle. So you think of an RCT to test the effect of manipulation on pain intensity in patients with back pain. And so in the sort of vertical axis, you've got the mean pain intensity in the group red, which is imagine it's the active, and the blue is the control. And near baseline, the mean of pain intensity in the active group was 52, the mean. So between 0 to 100, we asked everybody in that group about their pain severity or intensity, and they gave us various values. Their mean was 52. 12.3 is the standard deviation, meaning this is how the 52 mean. The rest of the group, they have various pain intensity figures, which vary on average from the mean by about 12.3, more or less. We did the same in the blue group, which is the control, and their mean at baseline was 52 and the standard deviation 10.8. After time, we introduced the treatment, which is hair manipulation, and we measured their pain again. And we found that in the red group, the active, the mean after the treatment, after a certain time, was 30. It's lower. The pain has got better. The standard deviation is 9.4. In the blue group, the pain is also better, and the mean now is not 51, but 38, and the standard deviation is 10.2 now. So what happens here is that the treatment made some change in the outcome, which is the pain intensity. In both groups, the red group, the mean changed from 52 to 30. In the blue group or the control group, it changed from 51 to 38. So they both got better. What we're really interested in is the difference in the change, which means the mean difference, the difference in the mean change in the groups. And this will give us what we call the treatment effect. And the way we do that is by calculating the change in the active group, change from 52 to 30, 22 difference. The change in the control group from 51 to 38, 13 is the difference. And what we're really interested in, the 13 and the 20. And this is the treatment effect, is measuring the difference in the mean, 22 minus 13, and the difference in the mean is 9. You can do the whole calculation in a slightly different way, which is calculating the change from baseline. The change from baseline. Instead of saying 52 minus 30, you will get 30 minus 52. You, of course, will get minus results. And the final treatment effect is minus 9. As long as you understand what it means, meaning there is a mean reduction of 9 degrees on the scale of 0 to 100. And this is the treatment effect size, or the size of the treatment effect. And you will find this sort of the mean and the standard deviation very commonly reported in studies. So this is one example of a study where they report primary outcomes, and you can see on the top row observed and adjusted mean, standard deviation, and the columns. So the first column to the left is the time. So you can see the top of the table is of the outcome pain intensity, and the time 0 week, 6 week, 12 week, 18 week, and so on. And the second half, the lower half of the table, of the outcome pain as sort of functional disability from 0 to 100. And again, the time 0, 6, 12 week, and so on. The next columns, so you've got the first left half of the table is unadjusted mean and standard deviation for each group. And the spinal manipulation therapy 0, meaning they had 0 sessions, baseline. SMT6, they had 6 sessions. SMT12, 12 sessions. SMT18, 18 sessions. And then to the right side, you have mean difference. So if we, for example, take one example, if you take pain intensity at 6 weeks, the mean and standard deviation at baseline, SMT0, 34.5, standard deviation 18.4. And the pain intensity mean and standard deviation at 6 weeks with SMT6 at 6 weeks is 32.3, standard deviation 15.8. So this is the mean at 0, and this is the mean at 6 weeks, instead of 6 weeks. Now, when you look at the mean difference, you can see along that same column at 6 weeks, you now have the mean difference between the two, and the mean difference is 1.7. And that's what the mean difference is the difference between the means. There is another additional concept to understand here, which is standardized mean difference. And standardized mean difference is the same calculation which we made by calculating the mean difference. The only distinction here is that we take into account the standard deviation at baseline. So when we calculated the active, for example, and we said in the active arm, the difference in the mean was 52 minus 30, that gave us 22. That is the mean difference. When we calculate standardized mean difference, the SMD, we then divide the 22 by 12.3, which is the standard deviation of the mean at baseline in the active group. So we divide the mean difference, which is 22, by SD at baseline, which is 12.3. This is more accurate, and this is what is commonly used because it takes into account the dispersion, the variation, the SD, the standard deviation. This is an example of a paper. I'm just giving you the example here. It will be a really good idea if you look at the paper in detail, because here they reported the outcomes using the SND. That was calculating outcomes and estimating treatment effect size using continuous outcomes. What if we have categorical outcomes? In this way, we don't use means and SD, but we use risk and odds. So now we're introducing this concept of risk and odds. And let us think to illustrate these examples. A study or a trial of HRT as a treatment in 200 women with menopausal hot flushes found the following number of women still had hot flushes at 12 months. They started off having 100 in each group. Imagine that is the case. And at 12 months' time, in the control group, they didn't have HRT. 80 of them still had hot flushes, while in the HRT group, 40 of them had hot flushes. How do we calculate the risk and the odds? Now, the risk of having hot flushes in a group is the number of hot flushes divided by the total number in that group. So, the risk in the control group is simply 80 divided by 100, which is 80%. The risk in the HRT group, 40 divided by 100, 40%. So this is the risk of having hot flushes at 12 months after receiving treatment. And you can see, you can compare, the risk in the control group is higher than the risk in a HRT group. Odds. The odds of having hot flushes, the way you calculate that is number of flushes divided by the number of no hot flushes in the same group. So in the control group, the odds is 80 divided by 20, which is 4. And the odds in HRT is 40 divided by 60, which is 0.67. And you can see the odds, the concept of the odds, your odds of having hot flushes in the control group is 4-1, and your odds of having hot flushes in the HRT is, you can say, 1 to 0.67, or you can say 2 to 3. So it is less. How do we calculate now the treatment effect, which is the difference between the groups, not only describing in the groups? Let's talk about the risk now. We said the risk of having hot flushes in the control group is 80%, and the risk of having hot flushes in the HRT group is 40%. So we want to know what is the difference between these, because this is what treatment effect. This is, after all, we want to know what is the size of the use of HRT. We can tell that you have more risk for HRT if you are in control group than in the HRT. We want to know how much more, what is the size of the difference in here. And using the risk, this is how we calculate the treatment effect. You can picture this by using a table, so HRT and control, and this is how the numbers are there. There are two concepts to use to calculate the difference between the groups. One is absolute risk reduction, ARR. And because it's absolute, when you say absolute, keep in mind always you have subtraction. So it's the difference between the two, 80% minus 40%, and you have 40%. An absolute risk reduction, because it's subtraction, because it's absolute, the percentage remains. So you say 40% absolute risk reduction. So there's 40% reduction in risk. The other concept, it is relative risk. And relative always suggests division or proportion or ratio. So relative risk reduction, what's called relative risk or risk ratio, it's a division. And we divide 40 by 80, and you get 0.5. And what that means is that using the HRT reduces the risk of having hot flushes by half. So your risk of having hot flushes, if you had HRT, is half your risk if you didn't. You can turn it the other way around, say your risk of having hot flushes if you didn't have HRT is double or twice as your risk of having hot flushes if you were not taking HRT. One concept I want to introduce here, because it's related to absolute risk reduction, is number needed to treat. And this is calculated by 1 divided by the absolute risk reduction. You remember I said absolute risk reduction should keep the percentage, the 40%. So absolute risk reduction is 40%, not 40. And when you divide 1 by 40%, so you divide 1 divided by 0.4, not 1 divided by 40. And you will end up with number needed to treat of 2.5. You can round it to 3 or to 2. Number of women needed to be treated for one additional woman to benefit is 3. So you treat 3 women to have a fourth woman to benefit from the treatment in this instance. This slide is just to illustrate one point about the difference between relative risk reduction and absolute risk reduction. If you look at the table, the first column is the risk in the intervention group, and the second column is the risk in the control group. When you say the risk, meaning the number of hot flushes in the intervention group. So the intervention group, the first is 40. Having hot flushes in the control group percentage is 80%. So the relative risk reduction is 40 divided by 80, which is 0.5. Now, the second row, you've got the intervention risk. If we just said it is a 20 and the risk in the control group is 40, the relative risk reduction is 0.5 again. And the same, if you go to the third row, you've got the intervention risk is 10. The control risk is 20. We still have a relative risk reduction of half, 0.5. And if you drop 2 and 4, you'll get the same. The point here is that the relative risk reduction or risk ratio stays exactly the same no matter how the overall risk proportion is, as long as they stay comparable. The opposite is for the absolute risk reduction, because if you notice the absolute reduction from the top lower, it drops from 40% in the first row, 20% to 2% or 2% in the final row, meaning the absolute risk reduction is quite responsive to the overall risk. The number needed to treat also changed from 2 to 50. So the relative risk reduction is often the same in people irrespective of their level of risk. However, the absolute risk reduction will be greatest. So if you look at the top row is 40. The greatest in those who have most events that mean at the greatest risk. Meaning, the more risk you have, you will have more benefits. This is more representative by the absolute risk reduction rather than the risk reduction. Going back to the categorical outcomes and estimating the treatment effect size, now we talked about the risk. Now we talk about the odds. The odds, as we just said, of having hot flushes calculated in each group as the odds in the control group, which mean the odds of having hot flushes divided by the odds of not having in the same group. 80 over 44, or your odds in the control group is 4 to 1. Your odds in the HRT group is 4 to 6 or 2 to 3. Now, how do we calculate the difference between these two, the treatment effect or the size of it? By calculating the odds ratio, RR, which is the ratio of the odds. So that just makes sense. It's the division between the two. 0.67, your odds of having hot flushes in the HRT divided by your odds of having hot flushes in the control group, and you get an odds ratio of 0.175. What that means, the odds of having hot flushes if you were taking HRT is 78% less than if you were not taking HRT. And the 78% is coming from the other way remaining of the 100% of 0.175 or rounded to 0.18. Now we will be moving on to talking about statistical significance, p-value, confidence interval, and statistical power. A little bit of a more deeper waters as we go along. Now, we talked about how we conduct our study. We talked about bias, reducing bias, confounding, and all that. We still might worry that our study might have provided misleading results. And there are two scenarios or two types of this situation might arise. We might find a difference. So we say there is a difference between the groups of a treatment, whatever. That means the treatment was good or was effective or caused a difference. When in fact there isn't. In reality, there isn't. Meaning this is a result which is positive, but it's false. False positive. We call this type 1 error. It's a quite confusing concept, but I use this picture and I keep it in mind just to try to remember. False positive. You tell a man you are pregnant. Now, that is not possible. So the true reality, the true result should be negative. We say it's positive, so it's false positive, type 1. The mirror image of it, or the other side of the coin of this, is the opposite, which is we don't find a difference. We say the treatment didn't cause a benefit, didn't cause an effect. So we produce a negative result, but it's false. So it's false negative. The reality should be positive. Our study showed it negative. That's misleading. That is false. This is type 2 error. And again, there's a picture for it to remember, keep in my hand, is that when you find a heavily pregnant woman, and you say, we think from our test that you are not pregnant. Well, the reality is obviously she is pregnant. And so this is false negative. Now, after we've done everything, which is checking for the conduct of our study, we still have these problems. Why? Well, we did talk about bias, so that's one issue. The other reason why this might happen is chance. So you could do the most perfect study. You avoid, to the best possible way, avoid any bias. You have perfect conduct, and there is a still chance, a possibility that your study might come showing false positive or false negative results, purely because of chance. This takes us into the concept which is statistical significance. Now, statistical significance, it calculates the probability of chance, the probability that the result that you come out with is a chance. And if we repeat the study, we will not find the same result. So the probability that our result is purely by chance, and its result it's either false positive or false negative, meaning it is not true. So in other words, it calculates the probability that our findings are false positive. And this is what is called clinical statistical significance, the probability of having this worry that our results are false. And because it's a probability, it is given the letter P. P is. And by convention, we want this probability to be around 5% or less. That means less than 0.05. In other way, we want to say that there is only a 5% chance that a difference of the size found in our study would occur by chance if there was actually no difference in the whole population, a false positive finding. So what we're saying is we do a perfect study, absolutely perfect in all ways we could say this study is perfect. We avoided all bias, the conduct was perfect, and we say this study is perfect with a statistical significance of less than 0.05, meaning that we can be 100% sure that this could be false positive only less than 0.05%, minimally. And this is another way of saying it is that if we repeat the similar study 100 times, we by chance alone, not by a conduct problem, but by chance, we find a difference as great or greater than one we did find 5 times of the 100. So we accept that the result as being true, we will be wrong at most 5%, but we are right in 95% or more. And usually it says or more because the p is less than 0.05. So statistical significance, I guess, and putting it another way, is all about the probability of a chance finding that will not hold up in future. Significance does not tell us directly how big the difference was in the study, but it tells us about the future. And this concept it can appear a little bit of convoluted, but if we get your head around about what this is about the probability of finding that your results are wrong or false, and it should be minimum less than 0.05. What is confidence interval? This is another way of expressing or talking about statistical significance. One way we just mentioned was the p-value, probability. Confidence interval is another way, and it's better. It's a better way. What confidence interval does, it gives us a range. Not only tells us that the probability of our findings, if repeated in future, is less than 0.5, but it gives us a size, it gives us a range about the observed effect size. And this range is constructed in such a way that we know how likely it is to capture the true effect size out there in the world. And it's conventional that the confidence interval is set as 95%. 95, where is this coming? Remember, the p-value is 0.05, and this confidence interval is 95, is the other sort of the complementary to it, meaning 95% of the time the confidence interval contains the true treatment effect. You remember this, the p-value 0.05, that is the possibility of including false treatment effect, false positive. Here, the confidence interval is the mirror image of that, which gives us the 95% of the true treatment effect. And we will come to examples of that so that we understand, such as this example. If we look at mean difference here in the pain intensity outcome scale 0 to 10 of 3.2, the 95 confidence interval 2.8 to 4.1, it means that the mean is 3.2. So we found a difference in the trial of 3.2 on pain intensity. If we repeat that in the world again and again and again, we say that any trial or number of trials will look at the same treatment we looked at here, will find results in the range of between minimum of 2.8 and maximum 4.1. We found 3.2. And our true value, if this repeated again and again and again, we can tell it will be between 2.8 to 4.1. And that is the confidence interval. And the same thing you can talk about odd ratios, which is down there. the specified probability, which is 95%, it's called the confidence level. And the endpoints of the confidence interval are called the confidence limits. So the limits here for the mean difference is the lower limit 2.8, the upper limit is 4.1. If the confidence interval captures the value of no effect, this now represents a difference that is statistically non-significant. What does that mean? If we look at the number above, the mean difference is 3.2. So this is the mean. When we talk about mean, the point or the value of no effect is 0. So when there is 0, that means the mean difference is nil. So the mean difference we found here is 3.1. The confidence interval is 2.8 to 4.1. That range between 2.8 and 4.1 does not include 0, meaning all the findings that could be found in studies like our study will always find range of means which does not include 0. So that means our study is statistically significant. If, for example, we found mean of 3.2 and confidence interval of, say, for example, uh, minus 2.3 to 6.7. Minus 2.3 will, to go through the range to 6.7, will pass through 0, meaning if this study was done again, there is a chance, 95% chance, 95% chance or a probability that one study will find effect which is nil. And in that case, this is called non-significant result. The same thing applies for odd ratios. The only difference is the value of no effect is not 0, but 1. Because the odd ratio is a ratio. When the odds in the active and the odds in the control are similar, there is no difference, then the odds ratio becomes 1. So if odds ratio pass through 1, that means the treatment effect in that case is not significant. And when we look at the example above, days of work, the odds ratio 3.2, a 95% confidence interval is 7.6 to 0.3. 0.3 is less than 1, meaning in this example, the odds ratio 3.2 is not statistically significant because the range of the confidence interval includes the number or the value 1. And because the value 1 for odds ratio meaning no difference, that means there is a possibility a study will be done and will find no difference between between treatment and no treatment in this trial, and so there will be no benefit. Another information that the confidence interval gives us is the width of it. If it is narrow, capturing only a small range of effect sizes, what that tells us is that it tells us that we can be quite confident that any effects from far from this range have been ruled out by the study. And what that means is that if we look at the example above, the mean difference of between 2.8 to 4.1, the range are narrow. If we have a confidence interval of 1.2 to 16.4, that's wide. What it means is that if we use this study and we've done it again in the future, or if we use that treatment in the real world, we will have patients who are coming and showing a quite range of benefit, which could be minimum to massive benefit. So our confidence in the results in the future, or if it is used in the outer world, is not as good. If the range is tight, if say here 2.8 to 4.1, or even tighter than that, it gives us confidence that if this treatment is used or study is done again, it's very likely that we get very similar findings to what we found from our mean, which is 3.1. And so the confidence interval gives us a lot of information. Not only tells us whether uh, how true is our findings to the real true results. It tells us whether it's significant or not, but it tells us how far are we from the truth, whether the true effect size is captured within the range or not, and also the width of the confidence interval gives us information about how wide or narrow. And as a rule of thumb, usually tighter confidence interval come from large trials. Wide confidence interval comes from small trials. So when we see wide confidence intervals, we can assume and think this is a small trial. And these are the same examples, but illustrated visually here. So on the left, you can see the vertical line passes through 0. And this illustrates the pain at mean difference. And because it's mean, the 0 vertical line is the line of no difference. To the left of it favors treatment. To the right of it favors control. And what that means is that if we draw the figures, which is 3.2 mean, confidence interval 2.8 to 4.1, we draw like that. So the middle vertical red line, this is the mean, 3.2. The horizontal line is the range of the confidence interval. And you can see the information. The first is that it lies favoring the treatment. It's all positive, nothing negative. Second, the horizontal line, the confidence interval, doesn't include 0, doesn't go across the vertical no difference line, meaning it's significant. And thirdly, it's quite narrow. The horizontal line is small, it's not going all over the place. Compare that with the diagram on the right side. Vertical line, line of no difference. But because it's odds ratio, it's 1, not 0. And then to the left of it favors treatment. To the right favors control. And if we draw the numbers provided above on a red line, the vertical red line does the mean. It favors the treatment. However, look at the horizontal line, which is an arrow here. It crosses the vertical line of 1. It crosses the line of no difference. There is a chance, if the study is done in the future, it will show no difference. That is statistically not significant. And third information, look how wide. We put arrow here because if we draw to the point of 7.6, we might end up much more to the left of the slide, really, really wide confidence interval compared to the narrow confidence interval there. So that is information that we can obtain from here. This is an example of a results table, change in back pain score from baseline values interventional control in a randomized controlled trial. What this shows you really is that it just gives you an example of how mean change in scores and the mean difference with the confidence interval is illustrated here. And you can see, for example, outcome measure at 6 weeks. If you look, Roland Disability Questionnaire in the control group, minus 1.94. This is the mean change in score. In the intervention group, the mean change in score was minus 286. So that's the mean change. In the control, minus 1.9. In the intervention, minus 2.8. What's the difference between the two? 0.92. And we can tell from the numbers that this is in favor of the intervention. However, when you look at the confidence interval, minus 0.02 to 1.87. This is, we're talking about mean. Mean, the line of no difference is 0. The range is minus 0.02 to 1.87, meaning it includes 0. So we can tell this is not statistically significant because it includes 0. The final column, the same row, p-value 0.06. Now, we said we prefer that the p-value is less than 0.05, meaning we want to say the chance of having our results true, representing true results, not positive but false, in less than 5%. Here is 6%, and that is not acceptable. So this is another indication from the p-value that this result is not significant. And you can look at the rest of the p values, 0.09, not significant, 0.22, not significant. But then you got distress, 0.03, this is significant. And you can go through the rest of the table to look at these details. A good study should detect a significant difference between two treatments when a difference exists. Why would a study fail to detect a significant difference between two treatments? There really was no significant difference, so a true negative result, but at some instances there is a difference, but the study failed, and this is called, which we described earlier, as false negative result, and that's an example. So there is a difference, but we just couldn't detect it. This leads us to the concept of statistical power, which is the ability of a study to detect a difference when there is a difference to be detected. Meaning, if a difference is there, we really have to provide power to our study. We make our study powerful to detect that. Otherwise, we cannot detect it. Now, we set the power at a level and we say 80%. That is the customary. Sometimes it goes to 90% or 95%. In case you say you get that. Meaning is that we're able to detect a difference when the difference is there in 80% of the times, and we will miss it in 20% of the time. And as I said, 80 is something which is used, 85, 90, 95, also other cutoffs used. If statistical power is high, the probability of concluding there is no difference when in fact there is one goes down. So when the power is high, then we can really have confidence in detecting a difference when there is a difference. And this power is chiefly affected by the size of the effect and the size of the sample used to detect it. Bigger effects are easier to detect than smaller effects. Larger samples offer greater sensitivity than small samples. And one example I have in my mind which helps me understand this concept of power is this, and I hope it will help you. Imagine if I ask one of you and say, go to my room and get me please my red biro. Now, you go there and you find the room is absolutely messy. A big room full of stuff, there are pens everywhere, and I'm in a hurry, and so you come back. Now, there are two things that will influence the way you find the red biro, which is, first of all, is the size of the biro compared to the whole space, the room. If I had asked you to go and get me the chair in the room, and there are 3 chairs or 2 chairs, the chair is a big thing. You look at it, you find it, and bring it. So the size of the object that I'm asking you to bring really might affect the way or the speed you find it. And this is what is the treatment effect size. If I ask you to bring a biro, it's a small size object. If I ask you to bring a chair, it's different. The other way is, how often do you go? If you come back and you ask me and I say, oh, just look there, and you go and you come back, and the more you go, the more likely to find it, because it's a small pen and because of where it is. But if I give you one chance to go and I say you go there once, then the chances of you missing it will be less. The same thing if you come back and I ask another person to go and a third person, the more people go, the more times you go, the more likely that you will find the object I am asking you to bring. And this is equivalent to the number of people you are testing the treatment on, meaning the sample size. So the more people you have in your study and you try your treatment on and you check their blood pressure or pain or whatever it is, the more likely you are going to find the difference. If you test your treatment on 20 people, 100, 300, the larger the sample size, the more power, the more ability you are to finding a difference and not missing a difference. And if you are looking for a larger effect size, the more likely you will find it quicker and with a good power. So these are the two things that affects the power. This is what power is. Two things: sample size and the effect size influence the power. And so this is again just one example of a randomized control trial talking about power, and this is where you find it in the analysis section, and they say 90% power. So here 90% power at 5% significance level. Significance level talking about the p-value. The power is about the power for detecting, and they decided as 90%. There is another concept which is similar to statistical significance, which is a clinical importance. Statistical significance, if you remember, we mentioned in the context of confidence interval, is saying how significant our results are if the study were to be done again in the future, and if the confidence interval included the level of no difference, then we say the results are not statistically significant. If we repeat the study in the future, we will find no difference. We just found a difference in our study, but that's not statistically significant. Clinical importance is probably, as it says, is different. It's a clinical importance. You found a difference. And the difference is, say you found a difference for pain intensity of 0 to 100 of 2. And you say these tablets showed that if you take them, comparing the intervention with the control group, it reduces the pain by 2. And even if your study found that this is statistically significant, what you want to know, is this clinically important? And there is a concept which is, well, what is the minimum important? And for every measure, for blood pressure, for pain, for function, for depression, for anything, there is an agreed and some tested minimal clinical important difference. And this is the concept I'm introducing here, which is the minimum difference that is clinically becoming important. For example, you say, agreement or consensus or for pain, for example, is 10 or 20. So when your trial finds a difference of 7, Even if it's statistically significant, we say that's not clinically important. And this is an example. So this is a systematic review on surgery or conservative treatment for rotator cuff tear, and they have chosen these four outcomes: constant total score for shoulder function, American Shoulder and Elbow Surgeons score, pain visual angle scale 0 to 10, and short form 36. And they explained here in the data analysis about their MCID. And they said the estimates change in outcomes were compared with minimal clinically important difference, considered as follows: 10.4 points for constant total score. They already told you what is the MCID. So if their study found less than 10.4 on the constant, even if it is statistically significant, it is really not clinically important. 2 points for an American Shoulder and Elbow Surgeon score, 1.4 for pain visual analog scale, and 4.1 for short form health survey. So this is, when you read MCID, this is what it is. It is what is the minimum threshold to consider the results as clinically important. Now, we talked at the very beginning in part 2 of this session that the best evidence for treatment effect, really, the top of the hierarchy, the top of the pyramid, is meta-analysis. What is meta-analysis? It's simply an analysis which combines the results of multiple studies. Meta for in Latin is for above, beyond, is the top, is the higher. So you've got number of studies giving you results. You are combining them in a special statistical way to get the almost the average, not quite the average, but the combination of these to give you an overall result. And this can be visualized in what's called the forest plot. Called forest plot because it just was thought by people who described it at the beginning as looking like a forest. And this is just one example of a forest plot. You see it, and on the right side of this diagram is the forest plot, and on the left is the contents of it. And we will go through it to try to understand. And it's almost looking at how you go through a map or finding your way around things. So you start first of all by understanding what is this about. So you look at what is this. So here, as it happens, is the change in constant total score, and the scale is from 0 to 100 in a 1-year follow-up. So we're talking about a change in total score 0. What they put in the forest plot, first column to the left, usually they list the studies included, because forest plots are used for systematic reviews, meta-analysis of combining studies. So they put the names of next to them, they put the results. And here, difference in means. So we talk about means in outcome. Remember, means, and we have the mean here and the confidence intervals. Remember the lower limit, upper limit for each study. And we plot these along the lines. We have the line here circled, which is the line of no difference. Because it's means we're talking about in outcomes, the line of no difference is 0. To the left favors conservative treatment, -10, -20. And to the right favors surgery, 10 and 20. And what we will do now is we will plot the results along these lines in a visual way. And we put the mean in a square shape where the mean should be. Okay, 0.4, a little bit away from the 0, between 0 and 10. And the line, horizontal line, is the confidence interval. Lower limit, -5, upper limit, 6.3. And you see here that the rest of the results of the studies are plotted with boxes and the horizontal lines or the whiskers along the graph. One thing you notice is that the boxes are different in size. This really represents the weight or the contribution of the study to the results. And usually, larger boxes represents larger studies and small boxes represents smaller studies. One thing you also notice is that there are studies which wide confidence intervals and there are studies which are narrower or narrow confidence intervals. And there is a correlation between the size of the box in the middle and the width. Larger studies will have large boxes and shorter whiskers or short horizontal line. Smaller studies have smaller boxes in the middle and wide confidence intervals. And if you look at the studies, the first study, you can tell from the whether you want to read the figures or you look at the forest plots, is that the horizontal line passes or includes the line of 0, meaning that study, the top one, is not statistically significant. If you look at the middle one, this study is free of the line of no difference. So it does not include the 0, meaning it is statistically significant. And the third study is just beyond the 0. It is statistically significant, but it's got very wide confidence interval. So this is how these studies are plotted. You will get the meta-analysis. And the meta-analysis is the average, is the combination of the means and their confidence interval. And it is represented or plotted on the diagram not using boxes, but using diamond. The center of the diamond is where the mean is, 5.6, and the side angles of the diamonds represent the whiskers in the studies. And as it happens here, when you look at the figures and in the diagram, the left angle touches the 0, it includes the 0, meaning it is not statistically significant. So, as it happens in this study, according to this outcome, constant total score, that there is no difference between conservative treatment and surgery because the overall meta-analysis results include 0. This is how the study is included in the. And this is another one, which is the same study but using pain level on visual. This is another example of forest plot, just to really give you more examples so that you visually become familiar with it. So if we go very quickly through this, you look from the top, it's a comparison of platelets versus control. So we comparing antiplatelets like aspirin versus control. And what are we looking for? Outcome, all ischemic stroke or intracranial hemorrhage. So we want to see whether giving antiplatelets will prevent or reduce the risk of ischemic stroke. And the review is antiplatelet therapy for preventing stroke in patients with non-valvular atrial fibrillation and no previous history of stroke or transient attacks. And the comparison, antiplatelet versus control. And the outcome is ischemic stroke or intracranial hemorrhage. And we look at the diagram. The bottom half of it, you will have favors aspirin to the left, favors placebo to the right. And in the middle, the vertical line is the line of no difference. It's 1. Why 1? Because if you look at the top, it's odds ratio. So this is different from what we've just seen, which was means. And in the means difference, the line of no difference is 0. Here, because it's odds ratio, the line of no difference is 1. Now, the first column to the left, the studies, and we have 3 studies. There are abbreviations there. Next column, aspirin, N, N. The small n is the number of events. What are these events? This is the outcome. This is the ischemic stroke or intracranial hemorrhage, small n. And the large N is the total number of the sample size in this arm. And the next column is a placebo. So if you look at the first study, AFASAK1, aspirin 15/319, meaning that in this arm, for this study, 15 patients had ischemic stroke or intracranial hemorrhage out of 319. Compared with the next column, placebo. How many patients in that arm, in the placebo, in that study, had ischemic stroke or intracranial hemorrhage? 17 out of 315. And the same thing in the next study. 5/194 in the aspirin, 3/91. And the same thing you can do again in the third study. And they plotted in the middle, the treatment effect size. Where are the numbers for treatment effect size? To the far right column, the odds ratio. So here they calculated the odds ratio. What are the odds of having stroke or ischemic stroke or intracranial hemorrhage in the study one if you are in the aspirin group? 15 divided by the rest of 319, which is 304. And the odds in the placebo is 17 divided by 315 minus 17, which means 298, and so on. And the odds ratio for that study is 0.87. And the confidence interval is 0.43 to 1.76. And it's plotted in the middle with the blue box and the whiskers. And the same thing plotting the odds ratio for the second study and for the third study. And you can see now, looking at the middle, the odds ratio plots. First of all, you can tell that the boxes are different in size. The third lower study is the largest box, the middle study is the smallest, and the top one, the first, is the in between. And so that is related to the weight of the study contributing to the overall results in this review. And there is a column to the right which is weight. The first study contributing 34% to the overall. The middle study 7.6. The last study 58%. That's why it's got the largest box. The whiskers or the horizontal lines again tell you a story, which is the middle study, very wide confidence interval. It's a small study, and you can tell from the numbers it's a small study. Small box, wide confidence interval. And the third study, the lower one, larger box, very tight confidence interval because it's a big study. Now, the third information from the confidence intervals in this visual forest plot in the middle is you can tell that all of the studies included one in the confidence interval range, meaning they all were not statistically significant. And that is because they included the line of no difference, which is 1. And you can see the horizontal lines are crossing. And in fact, the overall treatment effect here, the meta-analysis effect, also crosses the 1, and that's why it is also not statistically significant. And you can tell from the confidence interval because it is 0.47 to 1.07. It includes 1. So this is how you get from the forest plots. A final information you get from the forest plots, it's what's called heterogeneity. And I put a red line underneath it. Heterogeneity is the variation in the effect sizes between the studies that are included in the review. Heterogeneity meaning the degree of variation. And it is usually measured by the I-square statistic. And this is given in percentage figures. If the heterogeneity is minimum, it is 0 or near 0. If the heterogeneity is high, meaning the studies are all over the place, some of them left, some of them right, they don't come in line. This forest plot had only 3 studies, and if the heterogeneity is 0, it's very good, I square. If we had sort of forest plots with more than just these, you can see sometimes they really line in one line or almost one line beautifully, but sometimes you get forest plots where the studies are all over the place and the heterogeneity is high. So this is what heterogeneity means, is the variation between the studies included in the analysis. So this is another example of forest plots, and really the point of this is just to show you the heterogeneity. Test for heterogeneity here is 81.5%, and you can tell looking at the studies how they are all over the place. Some of them on the left side of the node difference, some of them on the right side, and they are not going down in line. And sure enough, the heterogeneity is 81.5%. The rest of the forest plot is very similar to what we have seen. On the left, there are the studies aligned one after the other. The second column are the cases, n divided by n. The cases divided by the sample size in each arm. The same for the control. The middle is where they plotted the effect size, which is to the far right. And because this is odds ratio, these are the odd ratios and confidence intervals, and you can see the line of their difference is 1 because it's odds ratio. So really, even though this looks really busy, it might be intimidating when you look at it first, but when you really take your time and you look around at these details, then it all falls into place and it all becomes almost straightforward. This is another example of forest plots. The point here is to show you that sometimes you find series of forest plots, one above the other. It doesn't matter, the principle is exactly the same. All what they're doing here is that they are giving sort of subgroups. So you find here the top of the paragraph is higher quality studies, and they just decided to group these in one type, and then lower quality studies, and they group the same. The rest is exactly the same. You can see that how the studies are arranged, the intervention, and as it happens here, this is beans. So the vertical line of no difference is 0, and then you get the mean and the follow-up, and standardized mean difference. You remember we talked about the standardized mean difference. This is what they calculate here for the treatment effect size. And thank you.